please help us get started.
Thank you for the introduction, James. Hi everyone, I'm Songting Chen from TigerGraph. So today I'm glad to give a talk about assessing graph solutions for Apache Spark. And it is a joint work with my colleague, Victor Lee. So graph is really how we think, how humans think, right? So for instance, your profile, your interest is related to what products you browse, right? And what you browsed is related to what products you actually buy, right? And online retailers use such information extensively. For instance, they build a huge graph about people, about the products, and what kind of product they buy, they browse, and recommend the relevant products to you. For instance, they can find the people similar to you and find out what are the activities those people have, and recommend relevant products to you, right? And also, those online retailers as well as manufacturers, they manage their supply chains, right? In the graph, they manage all those dependencies, and they can easily find out whether the supply chain is healthy or not to identify any potential bottlenecks. And it's also used for cybersecurity, like fraud detection, where all the people account all the activities and all their interactions are put into the graph so that they can analyze all those activities holistically and figure out whether there's any fraudulent account or activities out there. So next time when you when you try to connect the dots in your mind, your brain is actually doing the graph computation work. So actually, the graph is being used a lot today. And if you go to Facebook or LinkedIn or all those social graph are used to power everything you see on their website, such as the newsfeed or the friends you may know, etc. And Google utilized this graph long time ago. They used PageGraph to power the web search. And as I mentioned earlier, Amazon or Wish, those online retailers using the graph to recommend relevant products to you. So let's look at what kind of, we know graph data is everywhere, right? We want to know what you can do about it. So early days, it's about PageRank. You run, massive analysis over graphs to compute, things like PageRank. And later on, Google proposed a programmable programming API such that you can write a complex algorithm using this API and execute that algorithm over massive amount of data. And today, things change a lot. So first of all, it's no longer about API because it's tedious to write code, right, to do certain things. And it's more about query language, so you can declaratively define what you want to do, right? So it's much easier, and the query engine knows how to optimize that, right? And we also know AI is booming, right? AI is always hungry for data. The more data, the better the prediction. And the graph data can provide a lot of interesting data which are hard to find from a typical relational database. And nowadays, the entire big data community are moved to more real-time because real-time data gives you better freshness, and the insights is more relevant, right? And last but not least, it's all about scale. So it's no longer just about the data size, right? It's also about the amount of queries. Right, so for instance, recommendation, there are millions of people accessing your website, so there's a graph computation going on at millions of queries per second. So, and a recent Gartner report shows that the graph database is booming at, it grows at 100% year over year through 2022. So having said what you can do on the graph analysis, let's look at the typical use case, right? So, early days is about PageRank, large amount of data, hours or even, not even days of processing. And now it's more about real-time computation, right? We have a real use case about spamming phone call detection. So you may think, it's about, when you receive a phone call at real time and we want to predict whether it's coming from a spamming phone call or not, right? So how graph feature helps here? Think about make a phone call to a number of other phones, right? And these other phones are maybe calling each other. So why it's helpful? Think about you and me. We are normal users. We are calling our friends, calling our family members. They may call each other, right? But for a spamming phone call, they may call a bunch of random people. They may not know each other, right? So by looking at the graph feature of those additional phones, whether they are calling each other, we are providing machine learning algorithm a lot more properties, right? Such that we find out it provides a lot more accuracy in terms of the machine learning prediction. And in fact, my colleague Emmer tomorrow will deep dive into this use case. And also the other use case about data center monitoring, right? So large enterprise today, it's very common to see tens of thousands of servers and runs very complex software stack on top of that. If there's anything goes wrong, you need some really experienced architect, knows everything to find out where the problem is, right? How Graph helps here, right? So we can model the infrastructure like this rack running on these servers, and this server running on this software, and this software communicate to other software, right? So if anything happens, we can look at the upstream to see what are the root cause that causing the problem, right? We can also look at the downstream, what are other applications also could be affected by this, right? So so then everybody is powered to do this diagnosis, right? And it could be even automated without having to have a dedicated architect who knows everything to do the work, right? And also, it's all about real-timeness. For the first one, the first spamming phone call detection, real-timeness will improve better prediction, right? For the second case, not real-time data probably is not even useful at all. And again, scalability for these applications is not only about data, it's also about high QPS, high volume of queries. So in this talk, we will specifically talk about Spark and the GraphX, which is a graph platform built on top of Spark. And we'll also compare TigerGraph, which is a native graph platform built from scratch. So in particular, we'll compare how they differ, right? What's the pros and cons for different applications, and also how they can work together to provide end-to-end solutions. So first, let's compare GraphX with TigerGraph. So this is the area of focus. So first, we will talk about the storage, how they store the data, and also we'll talk about query expressiveness. It's about how do you write, what kind of query you can run on the platform, and how do you write such queries. Right? We'll also talk about supported workload, last but not least, the scalability performance, which we all care about. So first, we talk about storage. So TigerGraph is a native graph platform where it has its own native optimized storage. We put a lot of compression, for instance, into the data. And for that, you need a ETL load process. For instance, you need to load the data or stream the data into. While GraphX is another paradigm shift where it doesn't really store the data. You query the data is stored elsewhere. For instance, it's in a Hadoop file system or another relational database, for instance. And at the query time, you retrieve those data on the fly. So there's obvious pros and cons out there, right? So one, for TigerGraph, for instance, you need to load the data once. So there's an initial cost with that. You need to have hardware, you need to have some sort of capacity planning, all this kind of stuff, and have an ETL process to load the data. And but once the data is loaded in, you don't need to load again, right? So for GraphX, there's no such initial cost. If you have a Spark cluster running and you already have your data source, you can already start to do some graph analysis. And now let's look at the query expressiveness. So you don't need to look at all the code, only look at the highlight part. So GraphX use an API-based approach to define graph algorithms. Let's use a popular PageRank algorithm. So let's quickly review what PageRank algorithm does. So for each vertex, it has an initial rank, for instance, being 1, and then it will distribute the rank to its neighbors. If it has 4 neighbors, then each neighbor will have an equal weight, which is a quarter, right? And for each vertex at the same time, it will sum up all the ranks received from its neighbors. And the algorithm runs on and on for many iterations until the weights kind of stabilize. And if you look at the left-hand side of this slide, you will see how this is being implemented in Spark, in GraphX, which is some sort of API. You define a message. In this particular case, you send a message from source to a vertex, to the target, which is the rank divided by the number of neighbors. And you also define the function to combine those messages. In this case, it's a simple sum function. So basically, for GraphX, it's an API-based solution. You define your algorithm in Scala language, and you fill in the details how you implement this basically API. So TigerGraph takes a different approach. So it's a query language approach, which is more kind of declarative. So if you look at the left-hand side, it's the highlight part. It's like a SQL, right? So there's a select clause, there's a from clause, and there's also a cum. And the from clause is about a particular edge you are interested. Here is about people follow another people, right? So a cum is what's interesting here. So it acts like an aggregate function at each vertex. So in this particular case, the target, the received score is summed up by the source score divided by its neighbors. So at first glance, it looks similar. It does exactly the same job, what PageRank needs to do, right? But if you look at in depth of that, there's no notion of messages, right? So there's no notion of, you don't need to define what messages should be passed from source to target or vice versa. You just define exactly what you want to compute in a formula, right? So target score equals, sum up the source score, right? And the benefit of that in this, any query language that is declarative makes it really easy to add more and more complex things to it, while the system understands what this does and can do the optimization, which is kind of transparent to the user. So we can easily extend this PageRank algorithm by adding more computation to it. For instance, we want to compute the max rank, right, from its neighbors, right? So we can, in this case, we just add one more formula. Say the target received maximum neighbor is, aggregated over all its neighbor score, right? So that's just one additional statement to the query where, you can even think about, let's add more complex stuff in it, like the target, the source can be computed by the target's rank or a combination of both, right? So in this case, the user doesn't need to worry about messages, how do we optimize the messages, and it's, something like that. These are all hidden system engine details that, engine all optimize those things without user even thinking about it. So this is really useful to define complex algorithms where, you just define what you want to do without worrying about all the messages, all the communications, all these fine level of details. So it's going to be very useful for complex algorithms. And GraphFrame is a sister project of GraphX, and graph analysis is more than PageRank or graph algorithms. There's another very important area of computation, which is pattern matching. So in this particular example, it's this pattern is about A follow the edge of AB to B, and B follow edge to C and D. So it's a chain of pattern or pass query. So as you can imagine, if you do it using API, using code, this could be really tedious job, right? Pattern matching, this pattern query makes it really easy to specify what you really want. And in TigerGraph, you can also do such pattern matching. And in fact, you can combine the pattern matching together with the algorithm and in a declarative way. Let's use the recommendation algorithm as one example. So on the right side of the figure, you will see, this is what we want to compute. So for a given user, we want to find out all the users buying the same product, right? And on the left side, the statement highlighted in red, this is exactly how we compute that, and this is the pattern. So from see the user, you buy a product, and we find the other users, also buy the same product. So the statement highlighted in red, it captures exactly this computation pattern. And on top of that, you can plug in additional algorithm to find out what the other products this user buy, and add additional ranking algorithms on top of that. So it's a combination of declarative pattern matching as well as algorithm. So make it really too easy to create some really complex graph algorithm or solutions. And also, we want to emphasize that the real-time updates in the queries can significantly improve the effectiveness of such algorithm. If the recommendation is refreshed every day, then you will miss all the latest purchase from this user or other users, right? So real-time updates is also crucial to improve the relevance of such graph algorithms. So, in summary, if we look at all the expressiveness of different systems, so GraphX, using API to design graph algorithms, and a GraphFrame is about declarative pattern queries, and the TigerGraph GSQL is a SQL-like procedure query language that is declarative on both the graph algorithm and pattern matching. So both of them provide powerful graph analytics capabilities. GSQL is a little bit easier to express if you have very complex graph algorithm due to being a declarative query language. So next, we look at what kind of query workload you can run. So GraphX is more about OLAP kind of workload. It can run very complex query over a very large amount of data. But it's not targeted for high QPS, sub-second query workload. And since it doesn't own the data, so it's not really, you can't really directly update the data in real time. So TigerGraph, it can support all of them. It's more about hybrid transactional and analytical processing. So next, let's look at the scalability. So Spark and the GraphX is well known for its being scalable and massive parallel processing capabilities. And the TigerGraph is also, is also designed from ground up with those MPP and the scalability in mind as well. So let's look at some benchmark results. So this is a PageRank algorithm running on the very popular Twitter dataset, which you will find in almost every graph paper. We run. So we start from one server, which holds all the data, to 16 server, where the data is partitioned across 16 different servers, and the algorithm is running in parallel on all these 16 servers as well. So from one server to 16 server, the improvement in terms of latency is about 13 times. So it's not completely linear because there's a networking communication between those servers, so which cannot be reduced when you add more servers. This is very typical for graph computation platform, which we also observe from other platforms as well. So this is about analytics query or large queries scalability. So the next one is about point queries. What what is point query? Point query means we start from one vertex or two vertex, and then from these two vertex, we kind of scan, or we kind of follow the edge to 2, 3, or 4, or 5 traversals based on the needs. Right? So for recommendation or spamming phone call detection from one phone or one user, we may traverse many of its neighbors, 3 or 4 or more steps. Right? So for such algorithm, for such workload, it's not about reduce the query latency. They're already pretty fast, like tens of milliseconds. It's more about supporting higher QPS, right? Because there's a high load on, there's a many queries running concurrent from such system. By adding more servers, we can support more query workload or more QPS, right? So this is one benchmark on 3-step graph traversals, and from 1 server to 16 servers, it's about 11 to 12x more QPS we can support. Again, it's not linear, it's more sublinear kind of improvement because there's also network communication involved. So next, let's look at the performance comparison between GraphX and the TigerGraph. We use the PageRank algorithm. So, we use the edge partition 2D for GraphX, which is the best partition solution for this PageRank algorithm. And there are 3 things we can observe in this benchmark. First, which is marked as the brown color. So there's pretty significant loading data in the graph partition overhead for GraphX, which is expected because the data is loaded elsewhere, right? So it should be fine when you run it once, but if you run it many times, this cost could be significant. So that's the first observation. So the second observation is the memory overhead. So we found out that GraphX need a minimum 15 gigabytes of JVM memory to have good performance. And while TigerGraph use about 0.8 gigabytes of memory per server. And the third observation is TigerGraph also runs about twice as fast on the algorithm itself for PageRank. We think the difference is mostly due to the fact that TigerGraph is built from scratch using C++, and it's a native graph platform, so we can do any possible optimizations possible when we see fit. And this is the first benchmark. The next one, we try another popular graph algorithm, which is single source shortest path, which is from one source vertex. We try to compute all other vertex it can reach and compute the shortest path to all other vertex as well. So the results are kind of similar. There's one is the loading time is significant, and the memory overhead is significant, and also in terms of the real query performance. So here's the summary and the recommendation. We feel like GraphX, it's very, since it has no initial overhead, so it's a great tool for you to get results very quickly to analyze all available data you have to see if there's any interesting thing about your related to graph, right? And while TigerGraph is more about, once you identify something that is interesting, it's about high performance graph analytics, real-time transactional updates, high QPS kind of workload. So next, let's look at how Spark and TigerGraph can work together, right? So this is a reference architecture, how Spark and TigerGraph can work together. So Spark is a great platform where it can connect to other data sources like Hadoop, Oracle, MongoDB, all available data sources, and integrate them together. And it also has lots of building machine learning libraries, and you can even run TensorFlow, this kind of popular machine learning platform or framework on top of it. So how Spark and TigerGraph can work together, the first use case is Spark can help integrate all those data together, clean the data, transform the data, and store the interconnected data or graph into TigerGraph at scale. Right? So both sides are scalable. You can run many things, many integration tasks in parallel, and TigerGraph outside you have many servers. You can load the data in parallel. So that's the first integration point. And the next integration point is, as we have shown in the spamming phone call use case, where all these graph features can be captured from TigerGraph and feed into Spark for machine learning training. You can run building machine learning libraries or run TensorFlow, things like that. So that's the second integration point. And last is machine learning. So once you train the machine learning, you have the model available, then it's about prediction, right? So there are two options out there. So one is you can push the machine learning model into TigerGraph. So TigerGraph's GSQL is a Turing-complete language. It can literally do anything you like. So you can plug in the machine learning model as some sort of a user-defined function or something like that. Then at real time, we can extract the features and run the model predictions. Or the other option is we can run the model prediction elsewhere. For instance, we can run in Spark Stream, and at real time, Spark Stream can call TigerGraph to retrieve graph features, and together with all other data, and you can do machine learning ranking predictions out there as well. So that's kind of the high level 3 different ways you can put these two frameworks together, ETL loading and the machine learning training as well as prediction. So how can we connect Spark? Let's go down one level deeper. How can we connect Spark and TigerGraph, right? So we can connect that through JDBC, and we have an open source JDBC driver to do that. And we can do basically both ways. One is the read pass, and the other is the write pass. The read pass is about convert the TigerGraph's query result into DataFrame so that you can do further insights, or you can feed into machine learning algorithms. And you can also do the other way, which is a write path, where you can load the data frame, you can clean the data, transform the data, you have the data frame in memory or even files, and then you can convert them into Vertex or Edge and insert them into TigerGraph at scale. So the benefit of integrating Spark and TigerGraph together, we can take full advantage of the value that can be provided by the graph data and at real time, right? And we can combine all these data for deeper insights as well as AI, right? So graph is all about interconnections and all these different data. Why we want to integrate all those data, right? Because there's a connection between them. So graph is a natural way to capture such relationships. And it's also scalable in every step in terms of loading data, writing data out. Both sides can have many servers running in parallel, so it's scalable at every step. And we already have actual use cases running in this architecture. So that's pretty much it. I'm happy to answer any questions you may have.
All right. Thank you very much. If there's any questions, please. I'll run the mic to you.
In the architecture slide that you had, you mentioned how you can let the machine learning algorithms and models stay close to the data in TigerGraph. Is there a certain way they have to be implemented, or how can you deploy them into your TigerGraph cluster?
Okay, so are you talking more about training set or actual prediction?
The actual models, the prediction models.
The prediction. So we can have some kind of, we can have user-defined functions, and it's very flexible. It could be C++ program where you can plug in the model, and then once you extract all the graph features, you can run these extended libraries or models on the computed graph features.
And one other question. TigerGraph is not open source, is it? Is it a...
Yeah, right now it's not open source. You can use try out TigerGraph in two ways. One is we have the so-called developer edition, where you can download and you can try on your own server. And the other is the cloud solution, where you can, just a few clicks, we will set up the server, install all the software on it. Then you can use it directly so that you don't even need to have the server available.
Okay, thank you.
Yeah.
Hello. Pretty good talk. One question. What would be the comparison with Neptune from Amazon?
Right. So I think Neptune is built on top of key value store, I think. And also it has a query language called Gremlin. Gremlin is also kind of tooling complete compared to GSQL, but it's a little lower level. So the GSQL is a little bit more readable. So if you think over there, it's more SQL language, it's a little more readable. Gremlin is a lot lower level where it's each step you need to define what you want to do. And in terms of performance, in terms of scalability, I think both can have more servers running out there, right? And we also have benchmark, comparing the performance where you can find out on our website. Our TigerGraph's performance is a lot faster than Neptune at this point. Yeah.
Hello? Yeah. So can you go to the comparison from between Spark-X and So
this one?
Yes.
Yeah.
And also the read performance comparison. And I didn't see there's no loading data for the TigerGraph.
Yeah. Good. I think that's a very good question. So for TigerGraph, loading this data is about 3 times more than this number, which I didn't show because that's a one-time cost. And you pay the one time, you load the data, any subsequent queries don't need to incur this cost, right? And
so
it's a little bit.
Do you mean that all the data is loaded into the memory once, right?
Actually, it's not. It's actually, we load the data and also partition the data, and it's stored onto the disk as well.
Oh,
so,
okay.
which is why it's also taking longer time than this. The GraphX loading time, because GraphX is just loading data into memory. For TigerGraph, we also store the data onto disk because the data has to be persistent. Otherwise, if your server is down, all the data are lost.
Okay, so can you further explain the performance difference, especially for the read part?
Yeah.
Because you only say it's because TigerGraph used the C++.
Yeah.
Yeah, but is there any other reason?
Yeah, there's a lot of optimization in one is the storage. For instance, the storage is highly compressed. When the data is loaded, it's much smaller than the original data set. And also there's a lot of optimization put in the graph traversals. So to make it really fast to traverse not just 1 or 2 steps, but 3 or 4, even 5, or even more steps, which is crucial to gain really deep insights into the data.
Okay, thank you.
Yeah.
Some questions in the back.
Thanks. Is there a technical reason why TigerGraph is not compliant with the Tinkerpop API? Or is it just a strategical choice?
You mean this API, right?
Tinkerpop.
Sorry, can you say it again?
Gremlin, Tinkerpop API. Gremlin.
Okay. So it's more about make it easy for user to write graph algorithms, right? So The GSQL is tooling complete in the sense that you can do anything you want on a graph. Then it boils down to make it easy for user to write, right? For one, and the other side is about make the engine knows what you want to do and automatically optimize for that, right?
Yeah, it's not a critic about GSQL, but it would be actually easier for people that actually use Gremlin now to use TigerGraph if TigerGraph would have been.
I see. Yeah.
Yes.
Sorry. Yeah. So I think your question is about the query language between Gremlin and the GSQL. And right now, there's no automatic translation between the two query language. And also, there's an ongoing graph query language standardization where TigerGraph is part of the committee as well. So in the next year or two, there will be a standard graph query where you don't need to worry about the difference between different graph query languages. There's going to be a standard for that. In the near future. Yeah.
Yet another standard.
Well, that's it's significantly different enough from traditional SQL. Yeah.
All right. If there are any additional questions, I'm sure. Oh, yeah, that's right.
On the API side of TigerGraph, do you support GraphQL, or is it sort of a microservices architecture when it comes to application side of it? Because I get that you have APIs for your for Spark to write data to it, but for the application side, what sort of APIs do you support?
Yeah, very good question. So if we look at this architecture, so TigerGraph has a REST API where you can send the query requests directly to TigerGraph query engine. So on the right-hand side, you see there's Graph Insights applications. These are called through the REST API where you can extract the data out. Yeah, run the query, get the data out. Yeah.
Yeah, about the Neo4j. I don't know if you have study on Neo4j. How do you compare between TigerGraph and Neo4j?
So that's a very good question. I think it's about first Cypher support. I talk about Cypher, right? So there's a difference in terms of the query language, and also it's that's one. There's also about the scalability, performance, things like that. Yeah.
All right. Well, thank you very much for your time for presenting. Another round of applause for our speaker, Songting. If there are any additional questions, I'm sure you'll be happy to answer them in the back of the room. All right. Thank you very much, everyone.